Every once in a while, a single idea comes along that just changes everything. And back in 2017, a research paper from Google did exactly that for AI. It was called Attention is All You Need. And it introduced an architecture that is now, quite literally, the engine behind almost every large language model you've ever heard of, from ChatGPT to you name it. So let's dive in and really unpack how this one paper completely rewired the future of AI.
To really get why this was such a lightning strike, you first have to understand the problem they were up against. Before this paper, AI models handled language the old way, sequentially, word by word by word. Not only was this painfully slow, but it meant the models would often forget the beginning of a long sentence by the time they got to the end. The idea in this paper was completely different, a parallel approach, one that was fast and, this is the key, could understand the context of an entire sentence all at once. All right, so here's our game plan for breaking this down. We're going to start with a big problem they were staring down, what we're calling the sequential bottleneck. Then we'll get into their brilliant solution, this idea called attention. We'll see exactly how they built it into the now famous transformer architecture, look at the jaw-dropping results that set a new state of the art, and finally, we'll connect the dots and understand why this was a revolution. Okay, let's kick things off with that core problem, the sequential bottleneck. See, before 2017, the whole world of AI language models was kind of stuck on one single design. Everybody was using the same fundamental approach. And the paper itself just puts it so perfectly. No matter how many clever tricks people came up with, this fundamental constraint of having to process things one after another was holding the entire field back. It was a hard wall. And the thing building that wall? It was called a recurrent neural network, or an RNN. Just think of an RNN like someone reading a super long sentence by looking through a tiny pinhole, one single word at a time. It's trying its best to remember what it saw before, but you can imagine, by the time you reach the end of a long paragraph, you've probably forgotten the crucial details from the start. This one word at a time approach created some massive headaches. First, you couldn't parallelize it. You couldn't just throw a bunch of powerful computer chips at the problem to speed it up, because you had to go in order. This made training models take forever. And second, for information to get from the beginning of a sentence to the end, it had to travel this long, winding, step-by-step path, which made it incredibly difficult for the model to connect the dots between words that were far apart. So that's the problem. How do you solve it? How you let a model just see the whole sentence at once? Well, this brings us to the paper's absolutely brilliant central idea: attention. Now, the solution builds on a concept that was already kind of floating around in AI research called attention. At its core, it's a way for a model to weigh the importance of different words when it's trying to understand another specific word. It helps it zero in on what's relevant. Kind of like how when you read, your brain automatically highlights the subject and the verb to get the main point. But here's where the paper dropped the bombshell. They introduced self-attention. This is where a sentence gets to look at itself. Every single word can look at every other word in the very same sentence, all at the same time, to figure out what it means in context. This is a total game changer. It's not a one-way street anymore. The model can directly see the relationship between any two words, no matter how far apart they are. And this insight is what led to their incredibly bold, almost audacious claim. The title of the paper itself, Attention is All You Need. They weren't just suggesting a small improvement. They were saying you could throw out the entire sequential foundation of language AI and just replace it with this one powerful idea. So you have this wild new idea. How do you actually build a machine out of it? Well, that brings us to the architecture they created to do it, the transformer. This is the blueprint that turned the theory of self-attention into a reality. From a bird's eye view, it's an encoder-decoder structure, which was pretty standard for translation tasks. The encoder's job is to read and understand the input sentence, and the decoder's job is to generate the translated output. But the magic is what's inside, or rather, what isn't. They completely ripped out the old, slow, recurrent loops. Gone. In their place, just stacks of these new self-attention layers. So you might be thinking, wait, if it's not going in order, how does it know the word order? Great question. That's step one, and it's super clever. They add positional encodings, which are basically little mathematical tags that give each word a unique address in the sentence. Then, in step two, the encoder takes in the entire input sequence and processes it all at once. And finally, in step three, the decoder generates the output, also using attention to look back at what the encoder understood. But the real powerhouse, the engine that's truly driving this whole thing, is a mechanism called multi-head attention. See, the authors realized that just looking at a sentence's relationships from one perspective isn't enough. So instead of calculating attention just once, the transformer does it multiple times, all in parallel. The way it works is by using 8 parallel attention heads. And the best way to think about this is like having a committee of 8 different specialists all looking at the same sentence at the same time. Maybe one specialist is an expert in grammar, another focuses on who did what to whom, a third looks for poetic meaning. By combining all of those different expert perspectives, the model gets a much richer, deeper understanding of the text. Okay, so the theory sounds amazing, the architecture is brilliant, but the million-dollar question is, did it actually work? This brings us to the results. And the transformer didn't just work, it set a completely new state-of-the-art. The main test was machine translation. The number to watch here is the blue score. Higher is better. So look at this. The previous champion, which was a super complex combination of models, scored a 26.3. The new transformer model, a 28.4. Now look at the training cost. It got that much better score while using nearly 10 times less computational power. I mean, come on, that's a huge win. And let's be really clear about that 28.4 score. This wasn't just a tiny little improvement. It blew past the previous best result by over 2 blue points, which, in the world of machine translation, is a massive leap forward. It didn't just beat a single model. It beat these complicated, expensive ensembles of models. And the speed was just incredible. On a similar task, the big transformer model set a new record after training for just 3.5 days on only 8 GPUs. This was, as the authors put it, a small fraction of the training costs of the models it completely crushed. It was better, faster, and cheaper. The Holy Trinity. So that's the what. Now let's get to the why. What was the secret sauce here? What were the fundamental principles that made this architecture so unbelievably powerful? This table right here from the paper is maybe the most important visual of all. It gets to the very heart of the breakthrough. Look at the maximum path length for self-attention. It says 0.1. In plain English, that means the distance information has to travel between any 2 words is always just 1 step. It's like a teleporter. Now compare that to the old recurrent models, which were ON. That's like walking. The longer the sentence, the more steps you have to take. This one fundamental change, from walking to teleporting information, changed everything. And having this information teleporter had these huge knock-on effects. 1, it's massively parallelizable. You can process all the words at once, which makes it lightning fast to train on modern hardware. 2, that direct path between every single word gives the model a true sense of global context that older models could only dream of. And 3, as a nice little bonus, you can actually look at the attention patterns and get a peek inside the model's head to see how it's connecting words. The authors themselves knew they were onto something huge. They end the paper with this classic piece of academic understatement. We are excited about the future of attention-based models and plan to apply them to other tasks. This wasn't just the end of a research paper. It was the starting pistol for a whole new era in AI. And that's really the question they left hanging in the air for the whole AI community. This paper laid the foundation not just for better translation, but for the entire generative AI world we live in today. So the final question is a big one. If attention is all you need to master language, what else is it all you need for? Images? Audio? Video? What comes next?